Hello, everyone. My name is Abby Roth with the Education and Professional Development Committee at CETA. On behalf of the committee, I would like to welcome you to the webinar. Morgan Poland is joining us today. Morgan is a subject matter expert in contamination control, airflow visualization, and particle monitoring in clean rooms. Morgan has over 40 years of industry experience working in clean rooms in all industries. He has extensive experience working on clean room projects in over 40 countries and is a valuable resource for contamination control in critical environments for the electronics, aerospace, and healthcare industries. As a key member of MicroRight's expert contamination control team, Morgan is instrumental in developing proactive contamination control strategies through pragmatic risk assessment, particle testing, and airflow visualization. Morgan's broad experience in troubleshooting contamination issues has helped companies with remediation following 483s and warning letters. So this webinar will address airflow visualization studies, AVS, also known as smoke studies in clean rooms. Additionally, important international standards, industry guidance, and regulatory observations and concerns will be addressed. So our learning objectives for today, at the end of this, you should be able to examine how airflow visualization studies are defined and evaluated in international cleanroom standards, industry guidance, and regulatory expectations from the US FDA and global CGMP frameworks. Identify technical and practical considerations for planning and conducting effective smoke studies, and analyze real-world case studies illustrating the consequences of poorly executed airflow visualization studies and their impact on regulatory compliance and organizational performance. Before we get started, I'd like to share a couple of quick points. For those of you who have technical issues during the presentation, please use the chat option to communicate with the CETA office. For those who have questions that you would like to direct to the speaker, you can use the question box. And at the conclusion of the webinar, a copy of the presentation slides and a survey link will be emailed to you. We would appreciate if you could provide your feedback. We'll use that as we develop additional webinars. And with that, I will hand it over to Morgan to begin today's presentation.
Thank you, Abby. Thank you, everybody, for giving me your time and allowing me to share some of my knowledge, my passion, and experience that I have for the multidisciplinary field of applied science that is contamination control. Today's subject is cleanroom certification, more than a pass or fail, talking specifically about smoke studies or airflow visualization. We'll address airflow visualization, and as Abby talked about, what some of our learning executives were. I don't take any time to repeat that. As Abby said, I have over 41 years working in cleanroom contamination control on 5 continents. I've done projects in electronics, life science, aerospace, and defense, and I believe I have a unique perspective when it comes to contamination control because I spend a lot of time flying to sites. I'm currently calling in for this webinar. I am in Hyderabad, India, and I've been working on subject matter. We're talking about airflow visualization. Key points I want to stress when it comes to smoke studies or airflow visualization. The actual or physical contamination and control effect of a cleanroom or cleanroom airflow can only be effectively understood when it's visually represented. Airflow visualization is a science that's not unique to cleanrooms. An accurate visual representation of air patterns is required when testing medical product cleanrooms. An airflow visualization technology techniques can impact results and influence conclusions. The science of airflow visualization is not well understood, and I'll tell some stories and case studies about that. And this is based upon regulators' comments, observations, and some of these reasons include the lack of well-defined standards and guidance, inappropriate equipment on the market, and a lack of industry-accepted training. Smoke studies, like cleanroom certification testing and qualification, it's more than a pass or fail test. When we qualify a cleanroom, the data we get from the qualification in the cleanroom, be it particle count data, environmental monitoring, microbial counts, temperature, humidity, even pressure differential, we're meant to learn something from that and utilize that to maintain our controlled environments. Last thing, there's nothing clean about smoke studies. Airflow visualization, like filter integrity testing and recovery testing, these are extremely invasive tests. After we do the study, post-study cleaning is required. Smoke studies, airflow visualization is part of cleanroom qualification. I put this table together. It's part of a larger course that I do to compare how different industries or different regulatory agencies look at the cleanroom requirements. The column on the far left under tests, these are all the tests that are laid out in ISO 14644 for Part 3, cleanrooms and associated controlled environment test methods. And then the second column is general cleanrooms. The third column is required testing according to the US FDA, and the last column is GMP Annex 1 required testing. And as you can see, the only thing we need to call a cleanroom for general cleanrooms is particle count. And every other test is considered optional or recommended. However, international GMP and regulatory bodies have certain requirements they place on top of particle counting, where the US FDA requires filter integrity testing, air measurement, airflow measurement in terms of volume and velocity, differential pressure measurement, airflow direction and visualization, microbial, airborne and surface contamination monitoring, temperature, relative humidity testing. On top of that, international GMP, that would be EU GMP or the Pharmaceutical Inspection Cooperation Scheme, or WHO, Annex 1 or Annex 2 in case of WHO, require 2 additional tests that the FDA does not require, and that would be recovery testing and containment leak testing. So there's some differences, of course, between the expected testing from an international standpoint and the US FDA sterile septic guidance. But understanding airflow patterns in cleanrooms and controlled environments is an important aspect of contamination control. And I can't stress that enough, because it's exceptionally important to always remember and keep in our minds that cleanrooms work on the principle where the movement of HEPA filtered air is how we control contamination. We have different airflow patterns or expectations for airflow patterns in an ISO class 5 cleanroom than we would in an ISO class 7 or ISO class 8 cleanroom. And even still different when we get into ISO class 2, which is kind of the normative working environment in semiconductor electronics manufacturing. Today's webinar, we're going to be focused more on, of course, healthcare and pharmaceutical, medical device, and compounding pharmacies. Cleanrooms are complex environments, and the design of the cleanroom, the layout of equipment and furniture, the integration of equipment into the cleanroom may create areas with undesirable airflow patterns. And during our operations, personnel, equipment, material flows can create undesirable airflow that can act as a channel or reservoir. Because air is transparent, the contamination control effect of cleanroom airflow is better understood when it is visually represented. We're going to talk about this airflow visualization in this webinar. Airflow visualization, also known as smoke studies, when suitably conducted, can be used to qualify a cleanroom, a cleaner device, a RABS, or an isolator to evaluate the cleanroom's contamination control effects. And this allows us to understand the integration of equipment into the cleanroom, as well as airflow patterns at the interface between different clean zones. An example of that interface would be between a ISO 5 or a grade A environment in pharmaceutical manufacturing and the surrounding environment in case of a RABS, a grade B environment, or a grade C in the case of an isolator. Also important to understand the effects of door openings on airflow patterns. We use these studies to help optimize our cleanroom equipment, integration, and even furniture placement. Airflow visualization provides a visual tool for contamination risk assessment. It can help us determine risk-based environmental monitoring locations. Additionally, airflow visualization studies can help optimize operators' movements, standing positions, and can be useful for the development or improvement of standard operating procedures. Smoke studies, airflow visualization is a really important tool and can assist in operator training. In addition to that, airflow visualization can be a tool for troubleshooting contamination problems that can limit a cleanroom's ability to provide adequate contamination control. I first got involved in doing smoke studies back in 1987 when I was a young engineer working at a Department of Defense cleanroom for advanced photolithography. And I learned very early on in my career the importance of particle size and stability of particles. The first smoke study I ever did, we utilized cigarettes and Polaroid cameras in a Department of Defense cleanroom for making advanced electronics for the Department of Defense. Airflow issues can be behind intermittent contamination problems, media fill failures, environmental monitoring excursions, because why do qualified facilities have contamination problems? As I mentioned before, I got involved in doing smoke studies to troubleshoot contamination problems. And throughout the course of the 41 years I've been involved in cleanrooms, I've often been called in to help troubleshoot contamination problems. Smoke studies have been a very instrumental tool to help track down contamination problems. And in the last several years, I've been doing a lot more work in pharmaceutical manufacturing all over the world. And why do qualified facilities have contamination problems? And it might be because the contamination control effect of the cleaner may not be optimized. The locations of equipment, tables, shelves, even personnel positions or movements in respect to airflow may not be optimized. Contamination control considerations regarding the placement of HEPA filters, air returns, or even doors may not have been made. Other issues may exist, like blocked air returns. Equipment positions haven't been considered in respect to airflow patterns. Work tables in front of air returns. And that's something that's often overlooked. It's important to understand in contamination control, air returns are typically areas where we have greater concentration of contamination, because a simple thing that we consider, we pump in clean air into our cleanrooms, typically with HEPA filters in the ceiling. And then we want to suck out dirty air at air returns. So we don't necessarily want to be doing critical operations or contaminate or work on components that are sensitive to contamination in front of air returns. HEPA filters sometimes will short circuit into equipment inlets. I'll show some examples of that in case of RABS, BSCs, and even isolators. HEPA filtered airflows over personnel can flow into critical areas. And without understanding how air moves, we might make poor decisions or have poor placements for equipment or even our personnel. Adverse airflow patterns may exist. Air that moves in such a manner that could be a source of contamination. And the terminology the FDA uses in their 2004 sterile septic guides is a really good term to think about: air that can act as a channel or a route for contamination or a reservoir for contamination. Airflow over personnel or other contamination sources, such as the floor, then flowing onto products or critical surfaces, could be an issue. Air coming from uncontrolled contamination sources such as cooling fans, heat sources, refrigerators, or incubators. And the smoke studies didn't suitably characterize the contamination control effect of airflow patterns in the clean room being tested. One thing I really try to teach people when we talk about smoke studies is our goal in performing smoke studies isn't simply to do a pass or fail. Our goal in smoke studies should be to characterize the airflow patterns. And it's important to understand that anything that moves air or could move air in the clean room, we should understand, because if it's a cooling fan, or one of the things we see a lot in cell and gene therapy or ATMP facilities, are the use of refrigerators or incubators. These devices, refrigerators, freezers, incubators, these may have fans or move air. And particularly refrigerators and freezers have compressors. Those compressors are often at the top of the refrigerator or freezer. And those compressors only come on when it's under load. So often when we're doing our regular environmental monitoring, those devices may or may not be on. And typically they're only on when the refrigerator or freezer is under load. And these can be the source of contamination, sometimes some of the worst contamination in terms of fungal contamination. Sometimes airflow visualization testing may uncover cleanroom equipment design flaws, equipment integration issues, operator training gaps, or even cleanroom furniture locations or the selection of themselves. This is an excerpt from a video that's several years old, a smoke study video where the company, this is a compounding pharmacy, a 503B facility, that eventually was shut down. But the use of perforated tables, and that's something I always like to caution people. Perforated tables may be problematic. We often use these tables. We say we use these tables because we want the air to flow through the tables. But unless we're directly underneath a HEPA filter, some cases, based upon the design of the cleanroom, we may have air moving from the floor through the perforations. And in this particular case, we were running smoke underneath the table. And sure enough, because of the HEPA filter placement adjacent to the table, we were getting what we call a bounce back effect, and air was moving from the floor through the perforations in the table. And this was a source of frequent contamination and excursions that the facility had. So talking about, when we talk about smoke studies, and I use the term Annex 1 because Annex 1 is an international GMP guidance. In the US FDA uses their guidance for industry from 2004. I'm talking about the manufacturer and drugs, but we have standards, we have GMP guidance, and regulations. And everything typically starts with, I like to always start when we talk about it, is going down to the ISO standards. ISO 14644-3, test environments, the latest version is 2019, where it mentions airflow visualization testing and gives us some guidance. But there's not a lot of information in the standard. It simply talks about the methodology, but it does introduce us to tracer particle method as well as tracer particle generators. The US FDA sterile septic guidance requires that. International CGMP requires that. And then in the realm of the USP 797 for compounding, it's also required. There's other guidance. CETA has a really great document. Their application guide 14 came out several years ago. In addition to that, we have USP 1116, which talks about airflow visualization and introduces us to a very useful tool called the LNR method, the limitation of risk method, where we utilize airflow visualization in conjunction with particle counting to do a physical risk assessment. And I'll be doing presentations later, early next year, regarding the LNR method. In addition to that, we have a really very nice standard which came out April of 2025 from ASTM. This particular standard was worked out with a variety of international experts on airflow visualization. We did get input directly from the US FDA regarding this, and this standard guide for critical airflow visualization in critical locations. And I would encourage anybody engaged in smoke studies, particularly in critical areas, to get a copy of this particular standard, because it lays out some very good criteria that goes above and beyond all of the other documents I just mentioned. And it talks about neutral buoyancy quite extensively. I'm going to go through several 483s here, and I want to point out some points in these 483s, because I think it's really important if we're doing smoke studies with the intention to address regulatory requirements, whether it's USP 797, GMP Annex 1, or the US Sterile Septic Guidance. These 43s represent the FDA's critique of airflow visualization. This particular one talks about a smoke study failed to demonstrate the impact of a horizontal gap in the back wall of an ISO 5 laminar airflow unit. This particular 43 here talks about videos showing upward flowing of smoke along the RABS barrier. And an example of this, here we have an air return that is not completely blocked, it's partially blocked, but we have this upward movement of air, and this is an older facility where the laminar airflow hoods or laminar airflow unit above the enclosure is in the room, and it's actually stealing air from the room, and it creates this upward movement of air, which is not desirable at all. Another example, this is from a company here in Asia. The raw data video files were not available. And one of the things when we're doing smoke studies, we're recording smoke studies, it's very important to understand that we have to keep the raw unedited videos. If we're going to present or edit videos, that might be wonderful in order to streamline the review process, but the regulators may ask you to see the raw videos. And recently, a company, the edited video videos were edited so much that they tended to omit some of the flaws. And when the inspectors went to look at the raw videos, they found all kinds of issues with turbulence and did spaces that had been edited out of the videos that the customer had taken. Here's an example. We'll talk about neutral buoyancy. The grade A used A, and again, B4 in FDA when we do these 43s means it's redacted. So redacted base smoke generator. There was no demonstration to show the particles would demonstrate neutral buoyancy. And this is a term that is coming up quite a bit, actually quite a bit. And for example, I'll just tell a personal case history. I'm currently in India. I was actually in India in September. And what had happened was we got an emergency call in August. The company had just been visited by the FDA. The FDA didn't like their smoke studies. They called us up. We took a look at the smoke studies that the FDA had mentioned in their observation. Upon looking at those videos, I determined that the company had serious design flaws with their facility. We helped to work them remediate some of these facilities. We were on site in September doing the studies, and the FDA had gone to one of the company's other facilities where they had brand new isolators. And the FDA, when they're looking at the qualification of these isolators, refused. The US FDA inspector refused to look at the smoke study videos of the isolators because the isolator smoke study videos were done using a water-based fogging system. And the FDA said, it's water, it's not neutrally buoyant. Call us when you've got a suitable smoke study. So my 2-week trip turned into a 6-week trip, and where I had to go to the other site and we had to do the smoke studies for that. So the FDA is flagging smoke studies for neutral buoyancy. This 43 demonstrates that as well. Other things that the regulators talk about: objectionable airflow pattern, including turbulence and upward circulating air adjacent to an area where we have open syringes in the ISO 5 classified zone. Another thing the FDA talks about is the smoke generator, where the smoke output is pointed in a downward method. And this is the jetting effect, where when we shoot the smoke in a downward method or in the direction of the airflow, we can easily overpower the localized airflow patterns. And that, combined with a heavier than air fog, it's possible to make a toilet look like it has unidirectional airflow. And the regulators are waking up to this. Another point: the smoke generation device was not visible. During the majority of the videos. And it's important to understand, when we're doing smoke studies, it's important to be able to demonstrate or to show on the video that the entry plane, where the smoke enters the area of interest and where it exits. And that part of that would be to show where the manifold is or where you introduce the smoke. And then the smoke should flow through the area of interest and exit. And the FDA talks about this quite a bit. Pardon me, I'm having some trouble with Teams. It keeps popping up and blocking my screen. The volume of the smoke. The smoke should not be too dense. It should be dense enough to suitably visualize the airflow patterns. And again, if we have stagnant air, swirling air, dead air spaces, these are type of things that we should identify in our smoke studies. And all this comes from, coming to the US FDA Sterile Septic Guide 2004, they use the term in situ air pattern analysis. And they say it should be conducted in the critical area to demonstrate unidirectional airflow and sweeping action over and away from the product under dynamic conditions. And it's important to understand that facilities, even qualified facilities, things break down. Operators can become can become complacent, facilities break, and things can get shut down or age. In addition to that, in the U.S. Serial Stuff, the guidebook talks about clean air separation. And this is really, again, smoke studies are part of an overall comprehensive understanding of the contamination control effect of the clean room. The air, when we talk about separating clean air, differential pressure is really important. The FDA, as well as Annex 1, talks about a positive pressure between 10 or 15 pascals as a recommendation, but really important to understand that that only applies when the doors are closed. When the doors are open, we want our system designed, we have an outward airflow through the doors to minimize the ingress of contamination. And really, the only way to understand what happens with our doors, our clean room doors, is typically airflow visualization. It gives us a qualitative view of what happens when the doors open. And swinging doors act like a piston. When the door opens, it can pull air from one room and push air into the adjacent room. And the same happens when the door closes in reverse. Why are smoke studies so important? Because smoke studies show us the contamination and control effect. They can also help us identify situations where we may have poor airflow. Here's an example. This is a turntable in an aseptic filling line, a RABS enclosure, and this particular facility actually had an exhaust from the sterilization tunnel underneath the turntable. This is over 10 years. But to illustrate the fact that this was going on, we generated smoke in front of that exhaust. And as you can see, the smoke is moving upwards from the floor upwards, and the laser helps highlight the effect to make it very clear that we have this situation where particles representing air from below the floor are coming up to where the turntable is. And the laser just helps enhance that capability. USP 797 and pharmaceutical compounding lays out requirements for airflow visualization, particularly in the primary engineering controls, but also talks about using it in the secondary engineering controls, dynamic smoke studies, and then, of course, static smoke studies for the secondary engineering controls. Moving on to Annex 1, which the latest version of GMP Annex 1 came in on 2002, and this followed verbatim to PICS Annex 1, more of an international, extending beyond Europe into Canada. The US is actually part of PICS and other parts of Asia. And then also we have the WHO Annex 2. And Section 4.15 talks about airflow patterns with the clean rooms and clean zones should be visualized to demonstrate that there's no ingress of
Hi, everybody. Just hold on one second. It looks like we did maybe lose Morgan here temporarily, so hold tight. We'll see if we can get him back on here in a second. And as we're working to get him to return, just a reminder, if you have any questions, please enter them in the Q&A panel as opposed to using the chat function. Morgan will be able to check the Q&A at the end. So if you do have any questions, please use that to be able to ask the questions. Welcome back, Morgan.
Hello, sorry about that, everybody. Yeah, it's one of the problems. I apologize. The hotel, I paid for the high-speed internet, and yeah, I got cut off. Um, all right, can you hear me?
We can hear you. Just to share your screen again.
Yep, trying to get there momentarily. Where did I get cut off?
We were on that. I think you were finishing up this slide.
All right. So we're talking about Annex 1 and talking about how Annex 1 talks about doing smoke studies. And the question is, do I need to do smoke studies all my clean rooms? And we have to come back to what it says in Annex 1. And the question is, people often come with Morgan, do I really need to do smoke studies in my grade C cleaner, my grade D cleaner? Do I need to do smoke studies inside my garment cabinet? And the question always comes up is, or I like to answer, well, what does the annex say? What are you willing to define? And I'm a contamination control engineer. And my view of contamination control is our job is to understand contamination. So the first thing I would say in qualifying any cleaner, we should really consider understanding how the airflow patterns move in that room. And with that, that's important. We want to understand because we spent all this money building the cleaner and putting HEPA filters in. We have to requalify the filters and do the testing. We should understand how that air moves. In the case, I had a very long discussion with someone actually yesterday about the necessity of doing smoke studies in a garment hood, right? And garment hood, for those you may not understand, is very popular here in Asia, where the sterile clean room suits will come in, they'll be stored in a cabinet that has a HEPA filter on it. That HEPA filter often will either have a fan filter unit, or more likely they'll have what we call a LAF, a laminar airflow unit. And an LAF is not the same as a HEPA filter, and those you understand would appreciate this. And the point being, if this is where you're storing your sterile suits, and it's this special hood, in the gowning room where operators are gowning, that device moves air. And the air that the device moves may affect the contamination levels in the actual room people are putting on sterile suits. And it might create a condition where it may be blowing maybe blowing air in the direction of the door, which opens up into our critical zone, into our filling zone. And if we don't do a smoke study, we may not understand that. So it's always my argument is, again, our job is to understand the contamination control effect of all our rooms. Annex 1 lays out in section 4.25 all the tests that are required for testing a clean room, and clearly airflow visualization is mentioned to that. And people, sometimes make the argument, well, I don't need to do it for this room, or I don't need to do it in that area. And that may be very well, and you might be able to justify it, but really important to understand, if you're dealing with international inspectors, if you're dealing with somebody from another country, they're coming to look at your facility, we're making drugs where you're going to be shipping to their country, they're going to look at this guidance and they're going to read it verbatim. They may challenge you specifically on that. It's always something to consider, and you have to think about justifying it. Another important aspect about smoke studies is smoke studies should correlate with our air velocity measurements. And in our world of clean rooms, we've arrived at the 90 feet per minute, or 0.45 meters per second, plus or minus 20%. And that's always, remember that as a guidance value. And we typically do this, we measure air velocities typically 6 inches below our HEPA filters. And then according to the US FDA, some point proximal to the work surface and underneath our HEPA filters. However, whatever those velocities are, they should correlate and demonstrate, we should be able to demonstrate a sweeping action. But it's important to understand that objects below our HEPA filters are going to change our airflow patterns, and also it's going to affect our velocity. And I have this picture here. This is a photograph from a smoke study. This is quite old, but the company had a RABS enclosure for manufacturing drugs, and because the opening and closing of the doors to the enclosure, they decided to build an overhang, what we call an extended LAF, where they have HEPA filters over the doors so that they can open the doors to the enclosure to perform their intervention and setup, but they would have unidirectional airflow. But because of the design, we were having what was called a short circuit. And in this photograph, I'm showing the air velocity underneath the extended LAF, underneath the HEPA filter, 6 inches below, is 0.45 meters per second, or 90 feet per minute. But the airflow doesn't get delivered down to where these carts were, and that's where the company, the operators would stage materials, open materials, and move them into the filling line. So we had very little clean air getting down to where components were being staged and opened and then put inside the enclosure due to the short circuiting effect. And you can see in the picture that the smoke that we generate underneath the HEPA filters, again, we're 0.45 meters per second. That's where we're generating the smoke, is actually bending and short circuiting to the LAF above the operator's head. This is not a good contamination control effect. And this is a very common problem, which I run into a lot of older facilities, particularly utilizing RABS enclosures. And some of these companies, in order to stay operating, have to modify their facilities, and they will build an extended LAF where they'll have HEPA filters over the area where the doors are opening to prevent, to make the airflow better. Just one example. Here's another example of poor airflow. This is the grade B, grade A filling zone, ISO 7, where the operator is standing, and the enclosure would be an ISO 5 or a grade A environment. And when we did this test in the grade B zone, we noticed that there was a problem where you can see how the smoke is going off to the left of the screen. And that smoke is actually flowing through the RABS enclosure, even with the doors not open. And when the doors are open, it's flowing through. And the reason it's happening, I wanted to pause that. I apologize. The reason it's happening, I'll go here and I'll stop it right about here, is you'll notice the air returns right over here. This is an example where we had a relatively well-designed clean room. The RABS is okay, but the integration of the integration of the filling line, the enclosure into the clean room, creates the problem. And in this case, we had openings and the air returns were outpulling, and it's actually drawing air from the grade A or the ISO 5 environment, from the ISO 7 grade B environment through the enclosure to the air returns. And this resulted in, this test made it very, very clear to all the parties involved that they had to make modifications to prevent that from happening. And this was something that they didn't know, and they didn't know for several years that they had this problem. And what they were experiencing were intermittent contamination problems due to the poor integration. I want to introduce everybody here to ASTM E3379. This is the new standard I mentioned before. It's a best practice guide to airflow visualization and smoke studies. And this took over 2 years to develop. I mentioned before we had experts from all over the world participate in the creation of the standard, and we got direct feedback from the US FDA, where we delayed and modified the standard to address some of the FDA's concern for this. So I encourage everybody to get a copy of this particular standard. It introduces us to some important terminology, the critical zone, what the critical zone is, eddy currents, and also the concept of the entry plane and the exit plane, where we care about the smoke and where we don't care about the smoke. And we have to define where we start to look at the smoke, and when, for example, inside a filling machine, where we don't care about the smoke after it's gone past where our exposed products are, or critical components or product handling components are, as long as it doesn't reflux or bounce back. And also the concept of first air. First air is air that exits the HEPA filter or diffuser in a unidirectional manner that is non-contact at a contaminated obstruction or person. And people often make the claim or saying, well, if I have a diffuser, that's not first air. Well, sometimes we have to have diffusers in order to have unidirectional airflow to smooth out the gaps associated, the turbulence associated with gaps between HEPA filters. And it gives us insight into the in situ air pattern analysis, as well as what I could say the jetting effect or ejection velocity, where we're ejecting the smoke or the fog in a single direction. And then again, the standard also highlights the importance of neutral buoyancy. And this is a condition where the tracer particles, when diffused in the airstream, neither sink nor fall. And that's our goal. We want our tracer particles to be neutrally buoyant, as mentioned before from the FDA. Airflow visualization. Question comes up, when do we do it? Before I dive into that, I think airflow visualization should be part of the qualification of our critical processing equipment areas as well. ABS testing should be specified in user requirement specifications for new equipment. And I can't stress this enough. If you're buying a new RABS filling machine or an isolator, you want to make sure that your supplier knows, and they should know this, but you sometimes have to nail it home, that you're going to be doing smoke studies. And we may have to bypass optical sensors. I encourage, for new equipment, we're spending so much money and we have to do the factory acceptance testing. You should make the smoke studies as part of your factory acceptance testing, as well as the recipes or the programming allowing you to temporarily bypass the optical sensors that may be tripped by the smoke. Because, like it or not, you have to do smoke studies showing the equipment operating. And the response, and I've had one very large generics manufacturer that had hired me to supervise their smoke studies say, well, if the smoke triggers the machine won't run. That's a safety issue. We have an internal policy where we're not going to do the study. And my response to them was, the FDA doesn't care. You're making drugs. You have to demonstrate your equipment and your processes don't create turbulence. And then I'd like to talk next about, when do we repeat smoke studies? In the world of USP 797, it's pretty clear we have to do our dynamic smoke studies every 6 months, because in compounding pharmacies, it's a very manual operating process. It's a very simple, typically a very simple operation. We're doing the smoke studies to show that our bench is in control, and also to show that our process and our operators are following suitable aseptic technique. How often we do the smoke studies and the frequency should be determined in our contamination control strategies, but we may consider doing the studies if I start having environmental monitoring excursions, if I have equipment or cleanroom modifications. If I modify my cleanroom or my clean air equipment, I should probably repeat doing smoke studies, or a subset of that. If I have media fill failures and I don't know why, I may want to consider doing smoke studies to help diagnose media fill failures. If I have environmental monitoring sample location changes, I may want to do smoke studies to ensure that it's still that these locations are suitably located. If I have a regulator or a customer request us to do smoke studies, we're going to repeat our smoke studies. Smoke studies are also useful for training purposes, as well as if I move my equipment or my furniture around in my cleanroom, I may consider doing smoke studies. If I have a significant change to my HVAC, if my air exchange rates change, if my pressure differential changes between cleanrooms, or if I have any other type of changes, such change in line speeds, container sizes, SOP chains, or even the number of personnel in the cleanroom, I should consider redoing my smoke studies. Procedural considerations. I don't consider a person holding a wand and having an extra person holding a wand, in this case, inside a BSC, next to the operator, in situ air pattern analysis. That extra person affects the airflow patterns and can influence our results. In situ air pattern analysis should be hands off as much as possible. It's not always the case. In the case of horizontal flow benches, it's very difficult to do in situ without using a wand. And here's an example where the operator, the test personnel is holding the wand and injecting smoke directly over the operator doing this. And this particular smoke study was failed. I apologize. I had my headphone. I couldn't hear my phone alarm going off. Thank you, Kyle. So injecting the smoke directly over the area this is an issue. And again, by doing that, we're overcoming the local airflow patterns. And the last thing I'd like to finish would be talking about acceptance criteria. ASTM E3379 provides information acceptance criteria for all testing. The density of the tracer particle, the smoke, should be suitable for visualizing the airflow of interest. In terms of unidirectional airflow, we want to have first air sweeping action over and away from the product is demonstrated. And there should be an absence of eddy currents, vortices, or dead spaces. When it comes to equipment design, the equipment shouldn't block the airflow patterns, as well as in the critical zone. And the integration of equipment does not compromise first air. There should be a suitable pressure cascade from higher cleanliness to less clean areas. And when we're doing our interventions, the intervention should demonstrate unidirectional airflow to the point of the intervention at or near the critical area. And adverse airflow shouldn't act as a channel or reflux or channel or reservoir for contamination. There should be no refluxing. And with that, I'd just like to talk about neutral buoyancy. And here's just an example, a very easy way to demonstrate neutral buoyancy. This is using a passive pass-through. We smoke inside the pass-through. And in this particular case, it's a simple 10-second burst of smoke. The laser's there because it helps illuminate the tracer particle. But we'll see here, after the initial energy of the tracer particles being released, the tracer particles stop moving. And basically, it shows that the tracer particles are neither rising or falling. And I want to get to the question and answer section. I'll just speed this up. So after 1 minute, the tracers are still there, and we can see that the air is stagnant in this particular case. This is an example. The tracer particles aren't heavier than air. In addition to that, they are durable. They last for at least a minute. Our own internal processes we recommend is we want to demonstrate the tracer particles will at least be visible for a minute. And then we open the door. It's exceptionally clear that these tracer particles are going to show us the airflow patterns. The only thing causing them to move here, it's not heat, it's not gravity, it's simply the localized air currents. And with that, I guess I'd like to open it up for questions. I think I went a little bit longer. Are we ready for questions?
Yep, you can go ahead. Looks like there's about 15 of them in the Q&A, so you can click
All
that and
right.
open it up. You can answer away.
All right. So I wish I knew where that was.
So what I can do to start is I can, read one. It should be at the bottom of your screen where it's marked as Q&A.
She can't. I don't
Yep,
see Q&A.
because it should
Chat?
go chat, raise hand, share, and the Q&A would be right next to that. And if you can't see it, I'll just read it off.
Okay, I see it now. 14
Okay.
questions. All right. Here we go. So, James Graves, what are the issues can stem from overly high differential pressure between areas? I can't overly high pressure differential. That's kind of a question from left field. I apologize. Let me think about that. Let me answer some of the other questions. Which one is the right equipment for smoke visualization, tubes or a smoke machine? I believe that a smoke machine is the best equipment for doing airflow visualization. I'm not a believer in smoke tubes, but full disclosure, my company, we make equipment for doing smoke studies. Not only do the studies, we make equipment. So, you might consider me a little biased, but I believe it's much better to have plenty of smoke. Stephen, how many observers would you recommend? Finding a balance of enough to corroborate findings, but not too many to influence results within the clean room. Well, the observers don't necessarily have to be in the clean room. The observers can be looking through a window, or in the case with some of the systems out there available, like, for example, we use, they can be sitting outside or even in a conference room, and the smoke study can often be live streamed. But you at least need a customer representative on site with you, obviously the operators. I always encourage when you do smoke studies, it's very important to have the consensus. The number one thing when we set up a smoke study, one, I want to have the manifold or the smoke generation over the area of interest. And I want to make sure I have suitable camera angles. And always, before you hit record, you run that by the team. A smoke study should be done as a team, and you want the feedback from the customer. You want the buyout from the customer. In large pharmaceutical facilities, we may have 6 people. We may have representatives from QA, QC, manufacturing, engineering, and validation as part of that, looking on in the smoke studies. And that's the best way to approach, because I believe that's the best approach to have, because if there's an issue with the operator's techniques, the manufacturing or engineering or validation should be able to flag that. But you really want a consensus or sign off on smoke density, smoke position, and camera angles. Anonymous attendee, what level of cleaning do you recommend for a smoke study? And the question is 3X. And 3X, we call it 3X or triple clean. Smoke studies should be conducted during a shutdown. Very important. So we're going to do post-shutdown cleaning, right? Which would be cleaning, sanitization, and sterilization where appropriate. And not necessarily because of the smoke, of course, because the smoke are generating millions of particles, but the mere fact that we have people in there who typically aren't media fill qualified conducting the smoke study. We have cameras, tripods, and oh, by the way, we're simulating our operations, which in the case of the filling operation, you're going to simulate sitting up your filler, simulate broken glass, wiping up spills, doing corrective interventions. You're going to have to break the machine down and clean, sanitize, and sterilize where appropriate. From David, with reference to smoke pattern studies, have you seen an ISO 8 cleaner with sealing return? Absolutely, I have. I pointed out that the exhaust has to be lower sidewall returned so the particles can flow out smoothly. Absolutely. I'm a firm believer, and this is my opinion. It's very hard to convince me you have a cleaner if I have an air return in the ceiling, right? And the reason why that's so important, you don't want air returns in the ceiling because it's very difficult to remove large particles, macro particles, particles bigger than 5 microns. They're affected by gravity, and you'll never be able to get them to exhaust in a ceiling-mounted air return. And what it does is it creates this upward movement of air in the room, which I think is counterproductive to contamination control. Can you give your opinion of grade C rooms when aerosol goes to every dead airspace? Okay. Every dead airspace. So one other thing to consider is non-unidirectional full clean rooms are going to look a lot different when we do a smoke study than a unidirectional full cleaner. So when we do smoke studies in a grade C cleaner, we typically generate the smoke underneath the HEPA filter, directly underneath the HEPA filter, and observe how that air mixes in the non-unidirectional full cleaner. So you're going to see it move and dissipate throughout the room. But what we're looking for, 1, does the air mix? And 2, is there any condition in the room, any device that causes that airflow to either to accelerate? Is there any undiagnosed source of air movement? Is there a fan? Is there a heat source? And if you see the air accelerating, that's an indication, hey, what's causing it to change that direction so drastically in that portion? And like I said, this is why we do smoke studies in grade C, grade D rooms, at least as part of the qualification, under static conditions. From Fraser, what are your thoughts on multiple cameras during a smoke study? Absolutely. I'm of the belief, and at Microrite, we do smoke studies, we always deploy 4 cameras. Typically, 3 cameras are fixed, and we have a handy cam or a mobile cam. And we use that so that we always have good coverage. We can show a wide shot. We can show to the left, the right, or maybe above. And the intent is to be able to not just show the smoke, but the activity. I'm a big believer in multiple cameras. However, multiple cameras only help you if you can suitably report them. And this is why typically a lot of people like to use what we call a quad view or a multi-camera view, where whether I have a device that does it automatically or I edit the videos to create this, so I can look at all of the camera angles, they have to be synced, happening at the same time. And that is by far, in my belief, in my opinion, as well as a lot of my customers, believe that it's a much better way to do that multiple angles. But the approach that we take, that I take and my team take, is every single time we hit record, it's one test. I may have 4 cameras, but it's one test, and that test is the completion of all those videos looking at the same activity. Joseph says, you said HEPA filter typically installed on the ceilings. Do you have experience with HEPA filter installed in ducts or grade D like CamCube from Camfill Far? Not necessarily sure what CamCube is, but is there any issue regarding smoke studies and contamination downstream from HEPA filters when changing HEPA filters? Yeah, certainly. Removing HEPA filters, yeah, we can get contamination from that process, but typically when we do such an invasive work, we're going to clean up afterwards. From David, also in PICS Annex 1, it was mentioned air velocity at working zone to be 90 feet per minute. For example, in a closed system isolator, the work is carried out very close to the solid work surface. Well, let's go back to Annex 1. Annex 1 talks about an airflow range between 0.36 and 0.54 meters per second. That's 90 feet per minute, plus or minus 20%. And this is really important. That 90 feet per minute is a guidance value. When I have an isolator, I may have lower air velocities. What's most important, and Annex 1 actually expands on that, whatever that value is, it has to be justified, and I have to be able to demonstrate the sweeping action. So that's why whatever the value is, when we take our air velocity measurements, we want to define that. And you can define that in your protocol, what height or what distance you do that measurement away from the HEPA filter after, of course, the initial measurement, which is 6 inches below the HEPA filter. Julio, what smoke generating foggers used in the videos he showed? We had different videos and different smoke generators in those videos, but the majority of the videos that I created utilize the smoke generator that my company makes. From Lulama, EU Annex 1 specified guidance velocity of 0.45 meters per second at the working height, right? Rather than at the filter face. Actually, no. You got to read you have to read the USFDA sterile septic guidance where it says we measure 6 inches below the HEPA filter face and then proximal to the work surface. And this is a big misnomer. And I wish I had more time to talk about that, because I've seen companies have to install diffuser membranes in their RABs to get unidirectional airflow across the entire ISO 5 or grade A condition, because that diffuser membrane evens out the eddy currents between the spaces between the HEPA filters. Without the diffuser membrane, we don't have unidirectional airflow. I put the diffuser membrane in, it significantly decreases that air velocity. So what is important is unidirectional airflow in a sweeping action, and then, of course, air velocity. And if you look at USP 1116, it talks specifically about looking at smoke studies may provide us more information than looking at air velocity when we're trying to gauge things. So this is why we have both guidance talks about smoke studies, air velocity should coordinate. But getting attached at 0.45 meters per second at the working height is going to get you in trouble. I've seen companies rip out their diffuser membranes just to do their air velocity measurement to show, look, we're at 0.45 meters per second at the working height. And then they no longer have unidirectional airflow because they have gaps between their HEPA filters. So important to understand how the air velocity and that sweeping action are supposed to tie together, because companies, I've seen them wind themselves around corners or in knots trying to get that magical air velocity. And the point being is the guidance value.
All right. Morgan, I think that brings us to our time. So I want to just thank everyone who's made today's webinar possible. Thank you to Morgan for giving you your time, your insight on ABS. This was fantastic, and hopefully we'll be able to take some of these questions, maybe follow up with you and see if you can answer a couple of them for us for CETA membership. We want to thank just CETA in general and Capitol Hill Management Services for the technical resources, the Education and Professional Development Committee for continuing to drive this webinar series, and of course for all of you for attending. So there will be again a survey link and presentation slides that will get emailed to you. We will also have a copy of this recording posted to CETA's YouTube channel. So again, thank you to everybody for your time this afternoon. We hope you'll join us for future webinars. And Morgan, thank you again for your time.
Thank you, everyone.